Hi guys, I hope everyone are doing great there. So I'm Archana. I'm of Sri Venkateshwara College of Engineering, pursuing my graduation in 7th sem of EC domain. So today I'm going to discuss about the VLSI design under the topic of working of MOS transistor in different modes. So the different modes of an MOS transistor I'm going to discuss here, and the different modes can be of depletion, accumulation, and inversion modes. So why to waste the time? So I'm going to just discuss about the each and every topics and each and every modes also here. So what is meant by an MOS transistor? So basically it is known as MOSFET. So it is abbreviated as the metal oxide semiconductor field effect transistor is a type of a field effect transistor most commonly fabricated by the controlled oxidation of silicon. It has an insulated gate, the voltage of which determines the conductivity of the device. This ability to change the conductivity with the amount of applied voltage can be used by amplifying or switching electronic signals. A metal insulated semiconductor field effective transistor is a term almost synonymous with MOSFET. Another synonym is IGFET for insulated gate field effect transistor. So the main three terminals which have been consisted by an MOS transistor is gate, drain as well as source. So which is been represented as G, S and D. So here the body of an like a MOS transistor is of p-type substrate, and whereas in the source and drain will be consisting of n-type substrate, and over this n-type substrate as well as p-type substrate there will be a metal layer where it is been laid off, or where it will be accumulated over the substrate or the body of a p-type substrate. And the width of the width of the substrate is being given as W, and it is been represented as W as well. And here the source, drain and gate are been internally connected. When the power supply is been applied for the source or either drain, so when most of the time the source will be having the power supply, and then the connection will be internally taken off. So let us look after the working of an MOS transistor in accumulation, depletion and inversion mode. So here we are using the MOS capacitor. We can see that there are each and every parts which is been denoted by its own denotions. So let us look after each and every parts here. So what is meant by E naught? As we can see the E naught in both the materials like metal and semiconductor. So E naught is nothing but a minimum energy required for an electron to free itself from any of the material. Like here we are using metal as well as semiconductor material. So the electron need to have some energy so that it is free to move here and there in its material itself. And coming to the next point is phi m. Here the phi is nothing but the working function or a work that is done by an electron. So phi m is nothing but the work function that is being held in the metal material. So work function of the metal. This is the minimum energy or the energy difference between the Fermi energy of an electron in the metal to the vacuum energy level. And coming to the next part is phi s. The phi s is nothing but the work function that is been used in the, or the work function that is being undertaken by the electron in the semiconductor material. So it is similar to the phi m, whereas in the metal, the electrons in the metal. So here the phi s is nothing but the electrons in the semiconductor material. So it is the energy difference between the Fermi energy of the semiconductor of an electron in the semiconductor to the vacuum energy level. And then what is meant by X? So X is nothing but an electron affinity of the semiconductor. This is the energy difference from the conduction band minimum in the semiconductor to the vacuum energy level. Note that this energy does not depend on the doping, that is nothing but EC minus EF. So here the doping elements can be of different types, like example aluminium, silicon, arsenic, all those things. And then coming to the frequency band. So frequency band is nothing but the difference between the work function of the semiconductor to the electron affinity of the semiconductor. Now I'm going to discuss and I'm going to explain each and every mode. So the first mode is nothing but the accumulation mode. So in this accumulation mode, we can see that the accumulation is nothing but the Vg should be greater than 0. Accumulation is nothing but whatever the doping elements or whatever the electrons that is been present in the any of the material. So it should accumulate the holes in the p-type substrate. Okay. So here I'm going to explain it deeply. For an n-type semiconductor, as I already told, the n-type semiconductor will be having the electrons. So n-type substrate will be having an electrons, whereas in the p-type substrate it will be having an holes. So whenever the electrons will be accumulating over the holes, then there will be there will be a region where it is known as depletion region. Okay, so whenever the depletion region is been less, then it is like the current will be flowing on inside the material. Whenever the depletion mode is been increasing, then the flow of current or the flow of electrons from n-type substrate to the p-type substrate can be can be not. It doesn't allows the electrons to accumulate over the holes. Why? Because the depletion region is very wide, and now at that time the current does not flow. Why? Because it will be in reverse bias region or reverse biased condition. Okay, so now for an n-type semiconductor, when Vg is greater than 0, the metal Fermi energy is lowered, that is E is equals to minus QV. That is nothing but the electric field is equals to negative of charge of voltage. The insulator has an electric field across its and then terminates almost immediately in the near perfectly conducting material, but terminates over a finite distance in the semiconductor of the finite resistivity. The charge model indicates that the negativity charge must be created in the semiconductor near the interface. This charge is the form of electrons. Since n is equals to NIXP of EF minus EI of divided by KT, the electron concentration in the semiconductor near interface increases. This is called accumulation. So now let us discuss about the depletion mode. As I already explained in the accumulation mode only, so what is meant by depletion region or depletion mode? So depletion mode, it will be created when there is an accumulation of electrons from the electrons to the holes. Then only the depletion region will be created between two types of substrates or two types of bands. Okay, so the depletion is nothing but it will create a region between the two bands where the current will be flowing from through the depletion region, and where the operation of that circuit or operation of that semiconductor will be taking place. So now let us discuss about deeply what is meant by depletion mode in this concept. So as we can see the diagram over here, so depletion mode will be having depletion small, that is nothing but Vg should be less than 0. So here Vg is nothing but the gate voltage. For an n-type semiconductor, as I already told, the n-type semiconductor we are using here, when Vg, that is nothing but the voltage at gate, is less than 0, the metal Fermi energy is raised. That is nothing but electric field is negatively or terminated with the charge of an voltage. The insulator has an electric field across it, then it terminates almost immediately in the near perfectly conducting material, but terminates over a finite distance in the semiconductor of finite resistivity. Resistivity, nothing like the resistor is nothing but it will opposes the current. As we can see in the Ohm's law, that is nothing but V is equals to IR, and where R is equals to V divided by I, that is nothing but the current is inversely proportional to the resistor. So which tells that the resistor will opposes the current, and it is direct proportional to the voltage, where it will allow the voltage to flow. The charge model indicates that positive charge must be created the semiconductor near the interface. This charge is in the form of ionized donors. Since n is equals to, we can see the expression here, the electron concentration in the semiconductor near interface decreases. This is called depletion mode. So in the inversion mode, we can see two types of conditions or two types of semiconductors or n-type substrates here. So under these materials, there are two conditions. One is when the gate voltage is less than, when the gate voltage is equals to threshold voltage, and when gate voltage is less than threshold voltage. So first of all, we should be knowing what is meant by the threshold voltage. So here the threshold voltage is the voltage over which, depending on the technology, a certain phenomenon happens. That is nothing but the threshold voltage of a MOSFET, like as we are discussing about the transistor or the MOSFET. So we are discussing about the same thing. So I am explaining the threshold voltage with respect to MOSFET. Okay, the threshold voltage of a MOSFET is the value of the gate voltage when the conductive bands forms between the transistors, source and drain. After the threshold voltage, a large quantity of current begins to flow. So after when the gate voltage is higher, then only the current flows. When the threshold voltage is higher, then automatically there is a huge number of currents will be flowing out. So let us come into the points here. For an n-type semiconductor, for higher magnitude of bias, that is nothing but Vg is less than 0, the Fermi energy near the interface crosses the intrinsic semiconductor or intrinsic energy, and then the type of material swaps from n-type to p-type. We are using, first of all, we are using the n-type semiconductor here and our n-type material here. So when the inversion mode, that to be the condition when Vg is equals to Vt, then the n-type semiconductor or n-type material will be swapping to p-type material. The charge module indicates that positive charge must be created in the semiconductor near the interface. This charge is in the form of ioners, donors and holes. And coming to the second condition, that is Vg is less than Vt. For an n-type semiconductor, for still higher magnitude of bias, that is nothing but Vg is less than 0, the hole concentration continues to increase, resulting in a very high concentration of holes near the interface. This is known as a strong inversion. So now look up, we will be just looking after all the band diagrams of in the different modes. So the first one, the flat band. Here the DC voltage, that is the gate voltage, will be of 0. So the energy band will be in the flat position. And coming to the accumulation, that is Vg is less than 0. So here the Vg values will be more. That is less than 0 is the thing, but it is not in negative voltage. So whenever we apply the negative voltage, then it may results in short circuiting. So always we'll be applying the positive voltage here. So accumulation, so the energy band diagram will be in this form, that is the energy levels will be going down here. And coming to the depletion mode, here the threshold voltage is where the gate voltage is less than threshold voltage, but it is greater than what is that 0. Okay, so here the depletion will be taking out, and because of the depletion mode, the negative charge will be going here, so only the energy band diagram will be in this form. And coming to the last one, that is the inversion mode. So here the what is that gate voltage will be greater than threshold voltage. So here the current will be passing more, and here we can see the diagram of an energy band. So charge diagram. So here the Q represents the charge, positive, and here there is no current supply over here. So there will be no charge or there will be no flow of any of the current here. So the charge here it will negative and it will be positive, and here coming to the depletion mode, it will be in positive charge also, but the negative charge will be more slightly here. And then in the inversion mode, we can see the positive charge over here, and the what is that electrons. So here we are the electrons will be given here, and the negative charge will be actually very vast here and exposed acceptors. So here there will be in the large number of holes where the electrons can be accepted and where the electrons can be a donor, and then it can accumulate over these holes. Thank you everyone for watching my channel as well as watching my video also. I hope everyone understood what I had explained in today's session. So I hope the MOS transistor as well as the different modes where the MOS transistor will be undergoing, it will be very useful for your career as well as for your what is that competitive exams as well as for your main exams as well. So please do watch as well as learn more and spread the education for everyone, and let everyone be very successful in their life as well. So I hope everyone understood what I explained. Keep supporting me. Thank you.